Okay.
We got a variety of options here. So.
Yeah. Okay. So yeah. So I think that helps. So.
Dr. Vinod, you want to take it over? Okay.
Yeah, basically, no. I requested, even I have taken a permission from Dr. Peter to give us 2 or 3 minutes to set it up. No, the students, they are in a process to join. And I guess most of them, they have joined, and still majority of them, they are waiting to join in. So is it okay to start formally the session? Can we start it?
It's okay with me. With me, it's okay. Yeah, yeah. So yeah, okay. Whenever it works there. Yeah.
So yeah. So let me till the time others are joining. First of all, thank you so much, Dr. Peter, for accepting the keynote speaker acceptance for the ICCIKE 2021. And the moment we came to know it's a total different time zone, and it's a quite early morning, despite of that particular difference of the time zone, you have given the time for the ICCIKE 2021. It simply shows your passion, your determination towards the research and teaching and learning. Thank you so much. On the behalf of Founder President, Amity University, Dubai, on the behalf of Chancellor, Sir, Vice Chancellor, Pro Vice Chancellor, CEO, Amity University, we would like to welcome you on this keynote session. To the audience who are here about Dr. Peter. Dr. Peter Verman joined the Rice faculty in 1983. He served as a program director for the National Science Foundation from 2002 to 2005. From 2011 to 2012, and during the summer of 2013, Dr. Verman was a scholar in residence at VMware. In the summer of 2012, he was visiting faculty, software and system at the Intel Corporation. Dr. Verman is a senior member of IEEE, a member of ACM, a member of IEEE Computer Society, the New York Academy of Science, and is the president of various prestigious, and he is also the recipient of the various prestigious awards. He has been the editor of the Journal of Combinational Optimization since 2006, and he served as an associate editor of IEEE Transaction on Computers from 2000 to 2006. Dr. Verman's research interests are computer architecture, computer system, and high-end computing algorithm. Dr. Verman, we from the Amity University, Dubai, the student of Amity University, Dubai, and the many other students and the research faculty who have joined this session, we all are eagerly waiting to listen from you. Over to you, sir.
Okay, thank you very much, Dr. Shukla, for the kind introduction. If I may toot my horn a little bit, I have since that bio that I had put on the web, I have been elected IEEE Fellow for now a couple of years. So
quite an achievement. Congratulations,
well,
Peter.
No, thank you very much. Yeah, so yeah, thank you. Thanks, and for a very nice introduction. Is it okay if I stop my video while giving the presentation?
That would be fine.
Yeah, I'll have a still picture, but if it's a problem, I can just leave it on. But okay. So how do I get my slides on? Do I need to? Can I just?
Hello, sir.
Yes.
There is there is an option.
Oh, share screen. Yeah, share screen. Yeah. Okay. Yeah. Got it. Yeah, I didn't realize it was the same whether I joined
Dr.
or
Peter,
initiate.
I guess you are muted. We are not able to listen you in case you are saying.
Hello? No, I'm not.
I'm able to hear him. I'm able to hear him.
Yeah. Okay. Yeah, I'm not muted.
I'm able to hear you, Peter. Yeah.
Yeah.
Okay. Just check that side. The laptop.
Yeah.
So now we can see your screen.
Screen, wonderful, thank you.
Yeah.
Okay, and let me hide this floating meeting controls. Okay, here we go.
Please go ahead. Please go ahead.
Yeah. Okay, hi. So, well, we've had the introduction, but anyway, good morning still, or should I say, sorry, good afternoon in Dubai. And I thank you all for taking the time to attend. It is really my pleasure to join the conference, albeit virtually. It would be great if I could have been there in Dubai in person, but such are the times. Anyway, my talk for roughly the next 45 minutes or so is going to be on recent changes in technology that are impacting data center applications and data center architecture. So this is going to be a summary of some research results along with my joint work with my graduate students, Yuhan Peng and Chinwei Liu, both of whom graduated late last year and are now in industry doing different things. Okay, so just a little lead into the talk. Recent changes in technology have affected the way high performance and data center applications are being structured. Okay, it's now 15 to 20 years since the revolution or the inflection point in computing took place, where we had multi-cores and then GPUs and accelerator-based architectures. However, lately, the changes have been happening in the memory storage and networking areas, and that is really what I'm going to talk about today. Okay, this is, well, fortuitous or perhaps driven because of need, because modern applications, as we know, are highly data intensive and they have very stringent performance requirements, either in terms of the volume of data which needs to be transferred or stored or manipulated. And they also have strong latency constraints to get a real-time consistent response. So we are all familiar with the various types of applications and things like knowledge and deep learning and AI, all of which are very data intensive, right? Just 1 minute, please. I need to stop the video. Okay. Oh, I thought I would have a picture. Anyway, so an agenda for the talk. I am sort of broken it up as follows. I will first give some background on these new technologies that are both available and developing on the horizon. In the sort of anticipation that the background of people may be sufficiently broad that they may not be familiar with what's happening in this specialized area. Okay, so I will talk about the developments in memory, known generically as NVRAM, and then some of the developments in networking, known as remote direct memory access. Then, depending on the time, I'm going to see how these technologies have affected various applications. I will give one on a distributed storage server design, how the design changes quite drastically from that of a conventional design using conventional networking and storage technology, and the performance improvements that we are getting, both because of faster technology and because of the characteristics of the technology are changing the design. Then I would talk about quality of service in two environments. Once again, using an RDMA, some new problems arise which are not there in general server-based systems. And time permitting, I will talk about the distribution problem where I have the QoS not on a single server, but on a multiplicity of servers. Okay, so I'm going to begin by talking about so-called NVRAM or persistent memory. Of course, the heading of this title of this slide says SCM, which was Intel's early name for this technology that they were pioneering at that time, called storage class memory. But over time, it has changed, and now the generic name persistent memory will be used for it. Okay, so in since the early 2000s, there has been this lot of noise from a lot of the companies saying that they're going to have this new memory technology, which is going to revolutionize computing because of the change in the memory. Okay, so that went on. There were a number of companies, big companies, HP, Micron, a number of spin-offs and startups, which were trying to develop this technology. And it looked really that this was something which is not going to succeed. Great promise, but nothing was coming out tangibly. Then in 2015, Intel and Micron announced that they had been able to tame this so-called 3D cross-point technology for storage class memory. And they gave essentially a news release and some projections on how good this particular technology is going to be. Once again, things went quiet. Things were promised every 6 months or so, and it looked like, again, it's not really going to pan out. But finally, in 2017, Intel introduced what they now call the Optane memory. And what's shown over here, this was the first actual hardware that you could pass the board around and see the chip. This was like a replacement for SSDs or solid state drives. But based on a different technology. Normally SSD is based on the NAND flash technology, but this was based on this new 3D cross-point technology of Intel Micron. What came later, a year later, was a memory DIMM, like a DRAM form factor for using this technology. So essentially what they had now was a memory replacement based on 3D crosspoint. Okay, so why is this interesting? Okay, devices come and go, improvements come and go, but why is this something so worth talking about? Okay, at one level, there's just an evolutionary improvement in memory technology. And at one end, this can be seen as a replacement for DRAM, but with much better properties. So DRAM, as we know, is sort of reaching its scaling limits. And even though Samsung continues to push it forward, it is generally felt that the limit of integration is being reached, and we are not going to be able to get very much larger DRAM chips, which is a big problem for our multi-core processors, which are extremely hungry for memory. This technology has a much higher density, and therefore you can build or provide chips with a very much larger bit capacity than DRAM. It has other advantages by having lower power consumption. DRAM, as we know, needs to be continuously refreshed, while non-persistent memory uses power only when you are reading and writing, especially for writing. It has some drawbacks, that while the read performance is more or less comparable to DRAM, the writes are a little slower than DRAM, though as they say, with time, the technology will improve, and that should not be a major issue. There are also some write endurance limitations compared to DRAM, which for all practical purposes has infinite write endurance. But it's still not known what will happen as time goes on and the technology gets perfected. As while the write endurance would be less than that of DRAM, it may be enough that you're going to replace your server before this actually runs out. Anyway, so this is one dimension along which persistent memory was being pushed as a replacement for DRAM. And the other part was that it could also be used as a replacement for NAND flashes. So it has much better performance. Some of it is because rather than using the standard serial interface, it uses the much faster NVMe interface. And generally, they have said that compared to their own NAND flashes, it has much better performance. Okay, so this is great. It's nice to always be able to have things which are fast, but it is in some sense evolutionary. Yes, we have a faster device, we have a larger device, and we can tailor our applications and tune our applications to take advantage of this. However, that's not really why the buzz is. The buzz is because it has the potential for being disruptive to computer architecture. And essentially, the reason is that what we have is a device which is both DRAM-like, you can access it like memory, at the same time, it's non-volatile like storage. Power goes off, unlike DRAM, you can, the the data that you have written into this memory chip is going to remain even when the power fails. Okay, so therefore, there are several advantages which stem from this. So if you look at the conventional server computer architecture, we have really memory and storage as two independent islands. So the memory is shown over here consists of the cache hierarchy, L1, L2, L3, perhaps L4, and DRAM chips, which hold the memory state. Of course, there are two properties of this. One, that this can be accessed at a very fine granularity by the CPU. That's so-called byte addressable, byte, word, half word, or definitely a cache line, right? You can access things at the granularity of a cache line or less. On the other hand, you have storage, which has very different characteristics, shown as flash, solid state drives, or hard disk drives. And they have higher capacity, volume, but they are really block devices, and they are accessed not directly by the CPU, but they are accessed by going through the operating system. Okay, so what persistent memory does is it comes right into the intersection of these two. So looking to the left, it behaves like DRAM. It attaches to the memory bus. It uses ordinary load and store instructions that the CPU uses to access DRAM to be able to read and write persistent memory, and therefore it's extremely fast. And furthermore, it can be accessed at a very fine granularity, same as that of DRAM, right? On contrast, looking at the right-hand side of it as a storage device, it is non-volatile, like its other cousins, the blue cousins there. And the advantage is that it does not need this block access. All these other devices need to access data in this large granularity of blocks just for the internal structure. And that is a problem with modern applications, right? We do not really want to access large blocks of data. We are forced to do it because the storage devices require that for performance. But most of our modern applications, we want to just read a small social security number or a telephone number or follow pointers, my friend's friend, which city am I in. Small amounts of large amounts of small data is what modern applications require, which is really not the sort of access that is encouraged by traditional block storage devices. The other advantage is that there is no need for operating system intervention, right? Right now, we never do IO directly from a program. We call a library, which calls the operating system, which calls the driver, which essentially talks to the device and then filters the data back to us. Okay, so the enormous potential over here, one, in the fact that you can access it like DRAM, but treat it as if it was storage, right? So you do a store and then forget about it, it is there. You don't have to do all this operating system packing, unpacking, as well as function calls to be able to use it well. Okay, so that's all I'm going to say about persistent memory. And therefore, there's a lot of excitement that you actually have available now. Intel is actually shipping this now for several years. And just in December, they announced their platform future plans for their platforms, including a lot of enhancements that arise. I won't go into some of the problems of using persistent memory, but they are all sort of being ironed out by the architecture, the chip manufacturers in their high-end processor releases. Okay, so that was about persistent memory. Let me talk a few slides on this thing called RDMA, which is an acronym for Remote Direct Memory Access. And it is a way to be able to to transfer data from the memory of one computer to the memory of another computer over over an appropriate network. Okay, so it's the generalization of DMA that we are familiar with in a uniprocessor system, where the DMA engine copies something from memory and puts it into the storage or a network card, and vice versa. But here we are now going to use the same sort of conceptual structure to actually copy from the DRAM of one machine into the DRAM of the other machine. Okay, so there are many advantages for this. Clearly, you can do this very much faster. Once again, a big savings comes from the change in the software stack. Traditionally, you got to use something like a TCP/IP networking stack. It goes through several layers in the networking stack through the kernel. It gets copied in each of these layers, and when it reaches the other end, again, it's copied out all the way from the hardware till it reaches the application. Okay, so this is a way of essentially bypassing all that and saying a user program will directly write into the memory of the remote processor as if it were a local processor. Okay, sort of a little cartoon showing what happens. In general, you can bypass the CPUs, and by that we mean doing all the software manipulations and directly talk from memory to memory. Okay, this is not particularly new as a technology. RDMA has been there for a long time, but it has essentially been restricted to HPC high-performance computing platforms. And the reason was that because it was extremely expensive, and it used this proprietary InfiniBand protocol, which in turn ran on proprietary hardware by the company that made it. Okay, so it was there when you're buying a very expensive supercomputing machine. This was the small part of the cost, but was not suitable for regular commodity based computing. So lately, these things have changed, and RDMA is now available in the data center, and a lot of the data centers actually use that for their networking, or at least provide it as an option in their networking infrastructure. And that was because of developments in the RDMA implementations, where it does not need the InfiniBand infrastructure, but can be done over regular Ethernet as well. Okay, so that has the acronym ROCKY, and is now very, very popular. So essentially, there was the motivation or the catalyst to be able to actually employ this in a commodity data center rather than just stick it for high performance applications. So a couple of sort of concepts which are which help explain the applications that I'm going to talk about. One is how do we do the communication using RDMA? Okay, there are two modes which are used. One is known as two-sided RDMA, and in the next slide I'll show you what's called one-sided RDMA. All of them, as you can see, it's a very hardware-centric data transfer. So the RNIC stands for the RDMA NIC card, which is used to do the actual physical layer communication. And on the left-hand side, we have the sender. So generally the setup is as follows. You take some part of your memory. The application can take some part of the memory and register it so that it is now able to directly, so that the application can read and write that memory. And the RNIC itself can also read and write that memory. Similarly on the receiver side. So two-sided RDMA communication is somewhat like a synchronous rendezvous type of communication, but still it doesn't involve software, it involves only the hardware. So typically what would you do over here? What would the sender do if it needs to send? In the registered memory, it would write something into some buffer and then put a message into the send queue saying, hey, this is the address of the buffer, the size that I want you to send to the receiver. And the RNIC would automatically, when it processes that message from the send queue, take it and send it to the receive queue, or send it to the receiver. On the receive side, for two-sided RDMA, the receiver needs to post a receive in this receive queue saying, hey, I'm expecting a message, and when the message comes, write it to this address. So it would give a buffer address in its registered memory. And when the receiving RNIC received that message, it would copy it there and put a little message in the completion queue, which the CPU can either poll or be driven by an interrupt to know that a message has arrived. And then it can copy it from the buffer and do a receive buffer and do what it likes. Okay, so this is a sort of fairly, again, conceptually a standard way of doing communication, excepting that it's done at the hardware level rather than going through multiple software layers. Okay, so this is the major advantage of this, and it's quite fast. So note, we are now talking of microsecond latencies as opposed typically millisecond latencies when we're talking about communication. Okay, one-sided RDMA communication, which is also provided with RDMA, is something which is not there normally when you talk about doing communication, and it has several advantages. So the major difference is that with one-sided RDMA, the receiver is essentially unaware of the communication. Okay, so on the left-hand side, when the sender is, things look sort of the same. It writes a message, the data that it wants into a buffer, and then puts a message in the send queue telling the RNIC to send it. The difference is that in addition to saying which local buffer to copy from, it has the address of a remote buffer where it needs to be copied. Right, so the receiver is really not even aware that this communication has taken place. The two RNICs coordinate, the blue buffer, the data is taken from there, and when it reaches the receiver, is quietly and so-called silently written into the receive buffer, from where it can be, then it is up to the application to see where it is. As you can see, this is sort of different because how do you program in such a model effectively? Just like if a tree falls in the forest, no one is there to hear it. Has it really fallen? How does the receiver really know when data has been written into a buffer or not? When should it actually look? On the left-hand side, what are the addresses of the buffers that you need to use, and so on. Okay, so those are issues which arise and which have been solved as time goes on. But what you can see over here is that the receiver CPU is completely oblivious to what's going on. And it is a big change in the performance that you can get by not having to continuously interrupt the CPU to handle these messages that are coming in, right? So the CPU can be executing a whole bunch of stuff, and when the application has sent all its data, it can send one message saying, hey, here are some buffers which I filled up, go process them. Okay, so that's a sort of introduction to this technology known as NVRAM. RDMA. So what you can see over here is now, if I can put these two together, I now have something which is very powerful. What if the registered memory, say on the receiver side, is not regular DRAM as it was originally envisaged, but is replaced with persistent memory, NVRAM, which looks like DRAM, but is now persistent. Right? So you can think of, say, building a storage architecture now, which is extremely performant compared to conventional technology. So I have a cartoon shown in the bottom right where we combine these two into some sort of a storage architecture. We have a number of nodes, but within containing portions of the data. But instead of having your conventional hard disks and DRAM and your regular TCP/IP software stack, here things are going to be much, much more lightweight. Okay, the NVRAM is going to store my database, right, or whatever my data, persistent data that I need to store. And as we said before, this operates roughly at the speed of DRAM, right? So we're talking of hundreds of nanoseconds for doing a read or a write. Similarly, the interconnection between the servers or interconnection from a coordinator to one of these servers is through an RDMA enabled network. And so again, we're talking of microseconds of latency rather than talking of milliseconds of latency. Okay, so we are really talking of like 2 or 3 orders of magnitude potential change by combining these two technologies. Right till now, there was not that much of motivation because one or the other was the bottleneck. There's no point in speeding up the network too much for when the back end is going to be essentially ultimately be a slow storage device. Yes, there were improvements from disks to regular SSDs and from SSDs to NVMe SSDs, all of which were faster. But now you're talking of really order of magnitudes speed up both in the storage and in the networking. Okay, so this is the background for the technology changes. And I will take maybe 1 or 2, depending on the time, examples to show how we use this by example. Okay, if there are any questions at any time, please, especially during transitions, maybe while I'm transitioning, please feel free to ask a question.
Dr. Peter, there is a question which is posted by one of the attendees into the chat box in case.
Okay, yeah, let me see.
Will it be okay to take it at the end as per your convenience?
Yeah, okay, if I can see it now, okay.
I'm reading it out.
Yeah,
I'm
okay.
reading it out. So question number 1 is asked by one of the attendee having the name Venkata. He's asking, is NVM M2 chips better than most storage?
Well, the word better, right, means so many things. It has, you can have higher integration. It is, as Intel said, compared, if you put in the SSD form factor, because it's using the NVMe protocol, it's much faster than conventional SSDs. As persistent memory itself, there is really no comparison, right? We've gone outside the storage access times to something which is closer to DRAM access times, right? So in that sense, it's really good. And there's many factors involved. What about cost per bit and so on, right? That right now may be a little higher. It's still coming down, and that usually will come down with time. Okay, so all indications are that it is going to be a viable alternative or a replacement either for DRAM or both, right? It's not yet clear what the final architecture would be. Should the persistent memory act as just volatile DRAM as a backend for DRAM cache, or whether it should be the DRAM really is unnecessary, going forward. And for storage, there are issues like, there are other lower level issues which I haven't talked about, like how do you do security and so on. Yeah, okay.
Sir, can we take one more question?
Yeah, please.
Dr. Apoop Yadav, one of the faculty of Solar and Internet. The question is a bit of environmental related. The question is, what will be the impact of this technology on e-wastage?
I'm sorry, I missed the last word. On
e-waste.
Oh, yeah, electronic. Okay, e-base.
Waste management on the e-waste.
Oh, waste.
So basically,
yes,
if I'm able to,
yeah.
able to collect, maybe the kind of technology is moving,
Hmm.
the way we are moving into the more faster gadgets and
Yes.
into more downsizing is happening. And a lot of e-waste is continuously is also coming out of which is, I think the question is connected there. So what will be the impact of this technology on the e-waste?
Okay, it's a very good question. I do not know if I have an answer. I do not know if studies have yet been done on this. Just from the top of my head, if you're doing order of magnitudes better integration, you have less waste, right? When you throw away a chip, you are now throwing in, less of it away. But that depends on, that's in reality may not be true, because you also start, if I have this chip, I will start using that storage. It should not be that much different from what we do currently for getting rid of our DRAMs and so on, compared to the SSDs, and I think there is much less to waste over there. There are other issues like, well, I say power management is better compared to DRAM, right? So you're saving on electricity there, but the full question requires much more study. I don't think the technology has matured enough for people to address that, though they probably should in the life cycle.
What do you say? These are the two questions which were there.
Okay.
Right?
Yeah, wonderful. Yeah, thank you. Okay, so then I'll move on. Let me give one example of how this NVRAM plus RDMA influences the design of a particular type of application, in this case, a storage server or a distributed storage server. Oh my goodness, what happened? It's no longer responding to my clicks. Okay, here we go. Okay, so let me talk about a distributed storage system. And here is a sort of cartoon picture of a very conventional system using some type of solid state or hard disks. Okay, so what we have over here, shown over here, is a database where the data is sharded, fragmented in some way, and spread among the various servers in the distributed storage system. Okay, so over here I have like 5 shards, but in a typical distributed storage, for fault tolerance purposes, so you don't want to lose all the data saved on the server, you have some form of redundancy. Either you have replication, where that data fragment is replicated on many servers, or some of them try to use erasure coding, which has its advantages as well as disadvantages. I won't get into that now. So I'm assuming replication as a fault tolerance mechanism. So over here, if you have a replication factor of 3, I've shown the yellow shard being distributed among 3 servers so that I have a copy of it available in different servers. Right. Similarly, I have shown the various copies for each of the shards, and I made 3 copies of each of them. Okay, so this is great. It takes care of the fault tolerance issue to some extent. On the other hand, it will raise some challenges, essentially for consistency, which I'll see in detail. There's some more detail coming up. And at the same time, it raises opportunities. And the opportunities are, hey, I have copies of this data everywhere. Maybe I can do better than if I just had 1 copy of the data. Okay, but that comes with its own problems. Okay, so these problems are familiar with those sort of work in anywhere close to this area, but let me quickly, I want to show the difference in how things are done. So the first problem is that of what we call write consistency. So here I've shown 3 copies of some particular data item, and the problem is if I have 2 concurrent writes going on over there, we can end up with 3 values, 1, 3, and 5 in different copies of the data. And we need to have some sort of a protocol to make sure things work. Okay, in high-level databases system, this problem of consistency is handled by various types of protocols which exchange messages and coordinate. But at the storage level, you really cannot afford to do that. Okay, it is your basic service, read and write. You're not building a higher level transaction, which is doing all sorts of fancy things. And if you're going to delay that with a complex protocol, is usually not considered the way to go. So if you look at the way current distributed storage systems are implemented, what they do is they actually designate all the 3 replicas are not the same, but one of them is designated as the primary and the others as just regular replicas. And the point is that the primary is responsible for taking care of all the writes. So you cannot just write to any of the servers. All your writes for a particular data item like X have to be sent to the primary node, which would then queue them up and serialize them to make sure that there is only 1 value at any time, which is alive. Okay, but that's not enough. In addition to serializing it, the update needs to be propagated to the replicas as well. And so that's what's shown over here. And that's not an easy task, right? I mean, we have these replicas for the sake of fault tolerance. So before this write of a value on the primary node can complete, it needs to make sure that the replicas also have that latest value. Okay, so there are a number of protocols, but essentially, I think I will just give a little detail, something like a 2-phase protocol to indicate what's the problem. I will first send the value to all the replicas. The replicas will take it when they receive it and take it and go write it in some non-volatile storage, say maybe some disk buffer where it is safe, even if there is a power failure. Then they will respond to the primary saying, okay, I'm ready to commit this value. And if the primary gets back answers from all the replicas, or in some case, a majority of the replicas, depending on the protocol, it will then send another message back saying, okay, all you guys have agreed, go ahead and make that permanent in your database. And at that point, it would release the value to whoever wrote it. Whoever asked for write X equal to 3 to be done, it's only after it receives the acknowledgement from all the replicas, can it say, okay, it's committed, and tell the application you're done. Okay, so generally, therefore, this takes the time for doing a write is not simple when you go through all the steps. Okay, So that's right. And we said how it's taken care of. There is another issue which could arise when I'm doing reads. And so what's over here, I've shown the primary is updating the value to x equals 3. And it has propagated that to the replicas. And one of them has already received the propagation and has updated x to 3, while the other ones, it just hasn't reached that replica yet. Okay, so now if I do a read and I happen to direct it to the second replica, it will return the value 3. A little later, if I try to read the value, but I direct it to this other replica, it will return the value 1. Okay, so this is again inconsistency in reads, and it is handled in general in a data transactional system, like in a database, in different ways, right? Some database system will say this is okay. I will allow you to do this. I will so-called have a weak consistency model, and it doesn't matter if such a thing happens. There will be some out-of-band method where if it's an issue, it will be corrected. Something like Amazon saying, okay, I sold a seat which was not there, but I sold you a book which was not there. Okay, here's a $20 coupon, and that's it. We are all happy about it. Okay, but in a storage system, this sort of a weak consistency is really not desirable. It is the lowest level of data access. On top of that, you build applications where perhaps you can have weaker consistency, but many applications will require strong consistency as well. So the underlying base really needs to be the strongest possible. Right, so this is what we have over here, a strong consistency requirement, and it's defined quite simply. It says what the condition that's shown in that picture shouldn't happen. Right? If a later read, like the one number 2, returns a particular value, it should not return a value that has been that an earlier read that is earlier than that of a earlier read. Right? So if the earlier read returns 3, the later read should not return a value that was written before 3. Okay, it's what we would like to happen, but it makes it hard to do. So how do you do this? Once again, in the storage systems that are built, distributed storage systems, since you already have the notion of a primary, you do pretty much the same thing. So you send all the reads also to the primary. Okay, so you can see the opportunity cost in some sense is being lost over here. I have replicas, but there's only one node, the primary node, which is going to handle all the read and the write traffic. Okay. But given the technology on which these were built, essentially regular storage devices and TCP/IP type slow networks, trying to do a whole bunch of coordination messages didn't seem to make any sense, right? And that is why they have not been adopted in practice. Okay, so let me sketch over how these problems, for instance, are solved in a very different way when you have this new technology based storage system. Okay, so this is based on our paper that we had in the workshop, IPDPS workshop last year, and we have a larger version which is now out for review. Okay, so let me just say the major properties of this design. First, rather than funneling everything through a primary nodes, the writes and the reads can be made to any replica. Okay, so this right on the face of it, it reduces the server load because you can spread it out, and therefore improves performance, the latency, because you have potentially shorter queuing delays, especially for an all-read network. All-read traffic pattern. The concurrency is really proportional to the number of replicas, right? So with 3 replicas, you hope to get a throughput of 3 times what would be possible when you had to do it one at a time in one primary server. The second one is, the second point over here is not an advantage or disadvantage, it's just stating how it's done. We use write serialization by using distributed locking. So rather than using the primary to serialize the writes, over here we will actually do locking of a data item to make sure only one writer at a particular time. Okay, on a single CPU, this would be a sort of a natural solution. There are many writes that are happening on a single CPU. You do locking to that data item and serialize them. But trying to do this in a distributed way using conventional technology makes absolutely no sense because it's just too much of heavyweight messaging to be able to do this. But this is where a feature of RDMA, known as one-sided atomic operations, is extremely useful. What you can do is you have a lightweight operation, which you can, at the remote server, lock something in the memory of that server without even involving the CPU at that end. Okay, the second property of this is that the write propagation is done by using a lightweight form of two-phase commit. I mean, I still need to do that where I need to send the copies to everybody else and make sure that they all have it safe. But here, this is where I can exploit the property of NVRAM, right? Normally, I send the message is taken from the NIC and then copied into some disk buffer, and only then is the acknowledgement sent. All of those can be taken care of automatically by writing into an NVRAM buffer. And the acknowledgement comes directly back from the hardware. So I really have a very, very fast way of propagating my writes. I write into the remote buffer, the hardware sends me, okay, it's safe, and I'm done. Okay, furthermore, right, so both of these operations, the locking and the propagation, again, do not involve the replica server at all. Right, so if there's a coordinator which is doing the writes on the 3 copies, most of the load, or in fact all the CPU load, is on this coordinator. And different coordinators are doing their own writes. They're all doing it concurrently. The only load on the server is at the NIC card. The CPU can continue doing whatever processing it's doing without being disturbed. The time when the CPU is woken up is when everything has been taken care of. And you will have a much faster write commit. For the reads, we had to build a custom protocol because we don't want to do locking for reads. Reads are fast operations. You don't want to, even with a lightweight lock like done by RDMA, it's crazy. You have the classic problem. You have reader-writer locks, and then you have to make sure that readers don't wait for new writes and so on. You're going to destroy all the advantages that you were hoping to gain by the technology by building this very complex protocol on top of it. However, we were able to come up with a very simple lock-free protocol, which just uses one-sided RDMA reads. And on the next couple of slides, I'll quickly sketch it without. Okay, so let me just sort of animate how the write protocol works. So this is the sort of setup. I have the 3 copies. I have the RNIC, and each copy has a lock table, which essentially maintains a lock for at whatever granularity I want. So the coordinator is trying to write x equal to 1. It first sends this remote atomic operation saying lock x to each replica server. Okay, so CAS is compare and swap, a sort of a standard synchronization instruction, which can be done remotely with RDMA. Okay, what happens when the server gets it? The RNIC over there by itself as part of its functioning will go into this memory-based lock table and lock it if it's not locked, and in either case, return success or failure, that whether it was previously locked or not to the coordinator. Okay, all done in one hardware level network transaction. And if all the locks are successfully acquired, then the coordinator knows that nobody else is going to update any replica of X, and therefore has achieved a distributed lock on this. Okay, I won't go into the optimization. Should it be sending out all of them simultaneously, or to avoid potential live lock or thrashing, should all of them have a fixed order in which they go? Okay, it depends on the intensity of traffic. How about the propagation? So once again, as you can see, it's going to be very, very lightweight. The coordinator sends the value it wants to be written, right, of X to all the RNICs. The RNICs quietly take the value and write it into the NVRAM buffer, whose address would have been specified by the coordinator. And it would return an ACK. The moment you get the hardware ACK, the coordinator is ready to commit. When all 3 of them ACK, it is ready to commit, and therefore it is a very fast commit before it is done. It can then send a message. It is essentially now a backend message to each of the servers saying, hey, here's the address in your NVRAM buffer in which I have written the latest value. And when you have time, commit it to your database. Okay, I won't dwell on this too much. I just want to say this is just showing the in terms of a timeline how the communication looks. But essentially, you can see all this red portion is where is actual work being done, CPU involvement. It's all at the coordinator. On the right-hand side, when you look at the primary and the two replicas, R1 and R2, things are happening to them at the level of the network card, but the CPU itself is completely unaware of what's going on. Right? The only time when the CPU gets it is shown in step 5, after the data has been committed. At time step 4, the data has been committed, the client has been told, okay, you're done, you can continue, your data is safe. At that point, the replicas are updated, and then they can do a local update, copy it from the buffer into the actual database. But all this fighting and losing the contention, all that is done silently. Okay, it's not using up anybody's resources, but really just essentially the CPU of the coordinator, which may have to retransmit. Okay, quick couple of well, let me just talk about the read protocol. So the read protocol is necessary to achieve strong consistency. So it's pretty, it's not that obvious that it works, but it's quite straightforward actually. What the coordinator does is it does a read to any of one of the replicas. Okay, so some random policy to try and spread the load. It sends it to a random replica saying, hey, I want to read the value of X. What does the RNIC do? It will go read the current value of X and return that to the coordinator along with a version of X. So each data item at some granularity is time-stamped, saying what is its version number. Every time I update it, I increment the version number. After that, I need to check whether this particular data was locked or not. I'm not going to lock it. I'm just querying the lock to find out, hey, is it locked or not? And if it returns that it is locked at this time, then I cannot be guaranteed that it is safe. And so I take the safe path and abort the transaction and do the read again, essentially retry. If I do get past the lock, unfortunately, I'm still not done. It doesn't mean that just because it's unlocked now, it is safe to read it. During that interval, somebody else may have taken a later value. Right. Essentially, the time between these two operations, doing the read and doing the lock, they are not atomic. They are going to be two separate transactions, and I have no idea how far apart they are compared to what's happening on other nodes. Okay, so I need to do one more read. Once again, it's just a read. I need to read the version that is there after my checking of the lock. And that's the second version. And if my two versions differ, then again, it is possible that I've gone wrong. It's not guaranteed that I'm wrong, but it's possible that I've gone wrong. And to be safe, I abort and retry. Okay, in practice, when we do the empirical study, it doesn't happen very often. But the point is, I don't need to do any locking. All operations are one-sided. And again, happen silently without disturbing the server. And one can show that if you do both, if you get through both the lock and the version check, then the read is guaranteed to be strongly consistent. It's tempting to think that any one of them is enough and this is redundant, but actually both checks are needed, but that's fine. Okay, I think I should give you a quick summary of the experiment, some experiments. Okay, the paper has many more. So this one used a cluster known as the Chameleon cluster, which is there for experimental work. What it uses is an InfiniBand network. That's what was provided to us, not a Rocky network. But and the other difference was that we had to use DRAM to emulate NVRAM. It just happened that in that particular data center that we're using, experimental data center, you can either get servers equipped with NVRAM, or you can get them equipped with RDMA as of the time we did the experiments. And so fine. So we had to make a choice, and we said, yeah, it's what we want to check is how RDMA is working. Right? So we are actually, these experiments actually use DRAM as our storage backend. But I mean, the code is as if it were. Any checks that you needed to make for NVRAM are actually there in the implementation. We use a very standard 4 kilobyte Yahoo benchmarks for the storage system. And what we compared our system, which we are calling the Telepathy system, which my student named, comparing that with a traditional two-phase commit system where reads and writes are sent to a single server. We did some optimizations on the two-phase commit protocol to make it to take advantage of RDMA, so that we didn't have a we tried to make an apples to apples comparison. So we did some optimizations for that when we compared. What is the takeaway from this slide? Here we are showing the bandwidth in megabytes per second as we vary the percentage of reads in our workload. So on the left-hand side, we have an all read workload. And what you can see over here, our Telepathy is the one shown in yellow, and the conventional one shown in green. And it's what we would hope to happen, because we have 3 copies and we are able to read from all 3, we should get roughly 3 times the bandwidth. And we can see that is roughly 4 plus for the standard method, and roughly 12 plus, very close to 3 times. Another thing that you may notice is that the absolute values, if you look at it, we are getting something like 12 gigabytes per second, right? Which is just enormous. Think of trying to do this over a regular network, that is, right? So this is just crazy. Things are really out of the box when you're talking about these technologies. So we would expect reads to do very well, but we continue to do well, though of course less the more writes we do, because writes have to use up, have to be done synchronously on all processes. But continuously we do better than the conventional method, even at the extreme where it's an all write workload, because our writes are much more lightweight. We are able to get higher bandwidth than conventionally. On the right-hand side, it's the same experiments, but now we sort of skew the data. In the one on the left, we assume that the accesses are such that each node handles the same number of active primaries. While over here, we skewed it so that a lot of the requests go to fewer number of primaries, right? So they have to do more work. And as you can expect, the difference gets more pronounced. We tend to do exactly the same, but the baseline method starts doing worse the more load on the individual servers. Okay, so that's just shown over there. You can see the difference as it's skewed. The green, which was roughly 4, goes down to less than 2, about 1, and so on. You can look at the latency. That's the other important. On the left-hand side is, again, when I have the uniform load, it doesn't make too much difference in the latency, though, again, the yellow, which is our latency, is always lower than that of the conventional method. When you have skews, there's a big difference. Sorry, on the left-hand side is we are doing 100% reads. And when you're doing writes, and this is what we said, the write latency is very bad for the regular method. And you can see that over here as well, that the green bar is very much higher, both in terms of the average and in the tail latency, the 99% tail value. Okay, I'm going to skip this. This talks about the CPU efficiency. We say, suppose the CPU is loaded with something else, what happens to our protocols? And essentially you can see we tend to do well, while when you have a concurrent CPU intensive workload running on that server that you're trying to access, its performance for the data access really goes very, very low, while we are still able to maintain a fairly high processing rate because of the silent nature of the transactions. Okay, so that is completing that. I want to ask Dr. Shukla, how much more time should I continue?
Professor Peter, I guess the allocated time is approximately approximately about 2 hours. Maybe we can take it up last 2-3 more minutes to.
Yeah. Okay. Yeah. Right. Yeah. Yeah. Right. So essentially, yes. So this is what I felt that let me just really stop over here. Maybe just mention in the next 2 or 3 minutes what the problems are without going into any detail at all. Okay. So another application or more a situation and an opportunity that arises when I use these two technologies is to be able to do QoS on a single server. By QoS, I mean reservation. So the clients have some requirements. I want a minimum of 100 IOs per second. Client 2 says 200, and the other one says maybe 500. And you want to access this key value store in a particular server. How that is done conventionally is to interpose this QoS scheduler between the requests which come in on the left and the KV store. So the scheduler actually runs some QoS algorithm and decides which client's requests go in which order so that each one gets their reservation. Okay, now what we want to do is actually use this one-sided IOs because there's a tremendous performance advantage. I won't have time to show the slide when you use the one-sided IOs. And therefore, what happens over here, when the requests come from the client, the CPU is not involved. There's no scheduler that I can put in between. The requests go directly to the KV store and are returned, and the CPU doesn't even know that they have happened. So in this situation, how do you actually enforce some differentiated service between the clients? If I just allow the RNIC to do what it's doing, by default, it's actually very fair. If everybody is sending requests, it round robins them very nicely. And empirically, you can see each one will always get the same amount of service if they have enough demand. But what we want is differentiated service. Okay, so essentially, I will not even go into it. We have a solution where we move a lot of the effort onto the driver in the clients and only do a minimal amount of monitoring at the server CPU. Okay, so this is also a paper under review. I'm going to skip the details of this, but overall idea, we give everybody some tokens to say this is your reservation and you use them until you are exhausted. When you are exhausted, whatever is left, the remaining server capacity encapsulated as tokens, unserved tokens, or unreserved tokens in the server can be picked up by the client that has exhausted its tokens and removed and continue processing at that time. One subtlety is what happens if some server refuses to use its tokens. It's reserved so much, but it's not using it. I could let the server idle, but that's really not acceptable in practice. So we have a mechanism where clients who are not using their tokens are made to give them back, again, in a very lightweight manner to the server where somebody else can take them. So over here, the green guy is not using its tokens, and there is a mechanism where they are removed from the client and given into this global pool. And whoever wants them, in this case, the blue guy, could take them if needed. Okay, we have some experimental results over here. In fact, the slide over here shows the difference between one-sided and two-sided IO. So if you look at the one on the right, the blue bars represent in the steady state how many IOs per second, again in the millions, I can do if I use one-sided IOs, while the orange bar shows what happens if I use two-sided IOs. And you can see there's an enormous difference, which make it really motivating to be able to have methods which use this one-sided nature. This one shows that indeed the method works. The three bars shown over here for a particular client. The leftmost bar shows the reservation. The next bar shows what we get, and you can see it matches the reservation. And the third one shows what if we had a system without QoS, and it does not meet its reservation. Right. So, but what would it mean? It means that if I take another client, once again, the first two bars show that I meet my reservation, but the one without QoS is actually doing more. Right. So that makes sense. The capacity of the system is not less, but is giving it to the quote unquote wrong person. It's not based on reservations, but based on the access patterns. Okay, I'm going to stop over here. I will leave this third topic completely there. It deals with the issue of distributed servers, where the QoS has to be maintained in an aggregate form across many servers, while individually they have their while requests come individually to each server. Right. So the red guys which are queued up over here all of them have an aggregate requirement because that's the client, but it's just distributed. And at the same time, I have no control over how much the load and the demand in each of the servers are. So how do I do this? I can point you to the paper. We had a number of papers. In 2018, we had one method to do it. And last July, we had a really nice algorithm to be able to do this. And the important thing is that I want to show in the last slide over here. I will skip all that, how it's done. And that the fact that it works, let me just put the last slide over here. There are other ways of doing this optimization problem. But if you do something like a conventional linear programming type approximation to do this, if you look at the run times over here, they are just enormous, right? We're talking in terms of like seconds, 25 seconds for even a reasonable number of clients, 1,000, right? The sponsors wanted us to be able to do 10,000 clients. So LP didn't even run at that scale. And contrast, our method is running in something like 50 milliseconds, right? Even for 1,000. Our initial method, which was max flow, was a little better than the LP, but still it was not unacceptable because still the time was in the order of seconds. While again, as you can see over here, we are even less than that, 50 milliseconds. Okay, thank you very much for listening. I don't have a particular summary slide. I just want to say that this is really a very exciting time. Applications are right now very compelling and very very impactful. I think we are aware of them. And in fact, this conference, I was looking through the list, right? There are very exciting things that are being done in the application space. And it's one of the few times where the technology is also, changes in the technology are also gelling with it. And together they have really the chance to make a much more impactful and actually useful change than would have happened if sort of they had developed at different times. Okay, I will stop over there, take any questions. And once again, thank you for your attention.
I have a question here, just one. I know that in the beginning you talked about write, you tend to have a primary server where the write is done, right? And,
yes.
And then the remaining two replica servers, you take care of the synchronization. But now the different question, perhaps you've already answered it. Let us say the write is taking place on the primary server, but a read is happening from one of the replica servers. How do you ensure that you're not reading old data?
You're talking about our method or the one which goes through the...
Your method, because your method, I think, yeah, that's what I meant, yeah. How do you ensure that when read and write are synchronized appropriately?
Okay, so that, yeah, I will probably have to answer the details offline, but that protocol actually takes care of that. By doing the two additional checks after the read, checking whether it's locked and then checking that the version number has not changed, that would guarantee that write cannot slip through. It would either, okay, so.
No, my question is that when you're doing the write, are you also, when you say lock, you're only locking for other write on the replica servers. Yes. Not, what about read is what I'm wondering about.
Yes, so the read is, if a read comes at the same time, one of two things will happen. Either the timing of the reads and the writes are such that it will pass all the checks, in which case, right? But if it fails any of those checks, then exactly the problem that you're raising could have happened, which is why it retries. It doesn't, right? If either, yeah.
So it retries. Okay, it's not allowed to read at that point.
Yeah, we don't wait because it's all one-sided, right? So it's easiest to retry. Yeah.
Sure.
Yeah, and it works in practice. So yeah, so you may wait. I mean, but the wait could be at the client end, right? So it retry, it could put a little delay if it wants.
Sure.
Yeah. Okay.
Thank you.
Sure. Nice. Is there?
I don't think so. There is any further questions are there because we have picked up the questions in between.
That's right. Yeah, that's right. Yeah. So, no.
So for me, it was a complete for me, it was a complete deep dive, the very technical discussion for me. And I was able to relate something in between what I do into the networking, and the QoS factor is something which is quite similar when we talk about the migration from the IPv4 to IPv6. And that is where I was parallelly thinking on that particular parameter, because you was relating with the like the variable is with the client requirement, the variable keep on varying, and that is where the performance and the speed do also comes in.
Yes.
So for me, yeah, it was a very different discussion altogether. Thank you so much, sir, for your time.
Thank you. Thank you very much. And
thank you all the students and the faculty member who are here into this panel. Thank you, Dr. Anand. And on the behalf of entire Amity Education Group, and on the behalf of my colleague, Dr. Bhupendra, who is coordinating this session, thank you so much. And we look forward for the further collaboration and communication, which may help us for the further academics and research.
Sure. Thank you very much. And yeah, thank you, Dr. Bhupendra. I'm sorry I didn't mention you earlier.
Thank you, sir. Thank you so much.
Okay. Thank you.
With your permission, we will close it here now. Thank you so much, sir. Thanks.
Thank you. Bye-bye. Yeah. Yeah.
Thank you. Thank you, everyone.
Bye-bye. I'm leaving.
Bye, sir.